but it's but the sort of applications we had in mind were things like bottling lines for sort of fruit juices. So if you've got like glass bottles being filled with fruit juice going through at hundreds of seconds, just high speed things, when the juice gets injected in, it often creates lots of unwanted foam. So there are ways of getting rid of that foam, but I was sort of thinking it might be quite an interesting application if it worked.
Hey everyone, welcome to It's a Material World. We're the show that uncovers why material science will change the world. Consider subscribing and hitting the like button down below. It would really help us out. And before we get started, just wanted to mention that we have released material science merchandise for those of you who want to support us or just express your passion for MSE. You can check out more of the designs at itsmaterialworldpodcast.com/shop or by clicking the link in the description. All right, let's get right into it.
Our sponsor today is Johnson Matthey, a global leader in sustainable technology. Johnson Matthey's vision is for a world that's cleaner and healthier today and for future generations. Johnson Matthey's scientists use their deep understanding of materials, surface science, chemistry, and chemical engineering to design catalysts, advanced materials, and processes, tackling the world's biggest challenges, such as reaching net zero, enabling cleaner air, improving health, and using our planet's natural resources more efficiently. Johnson Matthey, inspiring science, enhancing life. All right. Hi, everybody. We're excited to welcome today's guest, Dr. Chris Hamlett, a Henry Royce National Outreach Officer for Material Science. His research career was inspired by the influence of surface on the properties of materials, and this has been the main thread of his research, which involved the physics and chemistry of surface process and assembly at a range of length scales. He now plays a key role at Discover Materials, a UK group whose goal is to inspire students and teachers about the world of material science. Welcome to the show, Chris. We're so excited to have you today.
Oh, thanks very much, David. It's great to be here.
So we wanted to start with your story, your background first. And I know you started out purely as a chemist, but you ended up making the switch to material science. And I know that chemistry is obviously a key component of MSc alongside physics. So can you talk us through exactly why you ended up switching to material science?
Yeah, no worries at all. Because I started university, as you say, doing pure chemistry. And then I found the course very sort of theoretical and not as applied as I would have liked. So I subsequently massively failed my first year, which I'm not afraid to admit. It wasn't the best start at university. But then I was told about this. I could do a course called Chemistry of Materials, and I thought, I'm not quite sure what that is, because at school in the UK we don't really do material science at school, or at least it's not labelled material science. So the first lab I did in the new chemistry materials course was getting a bit of metal, put it in liquid nitrogen, smash it in a Sharpie impact tester, which is basically a big hammer, and look at it under a very expensive electron microscope. And I thought, wow, I love this. So it's a case of, why didn't I know about this earlier? But yeah, again, it goes back to at school, because in the UK, in the equivalent of grade 6, science gets split into chemistry, physics, and biology, and you just get taught those rather than anything applied. So it was that sort of application of science that I loved, and especially the way that sort of chemistry and physics and bits of biology are all linked into material science. I found it fantastic. And so then after my degree, I went and did a PhD at Birmingham University, looking at the chemistry of surfaces. So you've got the surface of a material is the bit that interacts with the outside world. So it's a very small amount of the material, but it's almost sort of the most important part and the bit the world sees. So it's the bit that interacts, gives the material its color and how it sort of reacts with the outside world. So it's that sort of interfacial sort of chemistry, and there's lots of physics going on and biology that just really inspired me, to be honest, and how applied it can be.
Yeah, You mentioned the Sharpie impact tester, and then you were telling us even before this recording started about dropping pumpkins out of windows. So it seems like you love breaking things.
Yeah, who doesn't like smashing stuff?
Agreed.
but in a controlled way that you learn stuff from. So yeah. So yeah, there's a message there. Don't break stuff for the sake of it. Break it for a reason.
Yeah. I guess one question I have for you is that when we come in as students, it is hard to sometimes choose between different disciplines. I guess one thing I'm curious is, what do you think is like your biggest takeaway from chemistry that you're able to apply to material science, or what is the overlap between the two, and maybe a little bit of the differential of the two as well? Because it is kind of hard to differentiate the two when you know that they both involve chemistry, but to what extent does it?
Okay, so the bit that I really sort of took away from the chemistry and brought it to material science was the ability to change the chemical properties of that outermost layer of atoms. So the PhD work that I did, we were working with a group in mechanical engineering who were making tiny micron scale resonators. So they're basically little paddles that are a millionth of a meter in size. And my job was to change the surface chemistry of those in order to detect different species. So by species, I mean sort of like an analyte, for example. It's one of the ways that sort of drug detection can work, that you've got a surface with a given surface chemistry, and that can be used to stick certain, say, for example, viruses down. So that could be one of the most recent ones is the COVID tests and stuff. So you've got that. If COVID's there, it will stick and change colour of a test. But if it's not there, it won't. So that's down to the surface chemistry of it. So that's what sort of got me into the sort of sensing of side of sort of chemistry of materials, which was great. And then another application that I went to, I sort of like looked into during my further research, was how by changing the chemistry of a surface, you can change how water sits on the surface. So it's known as wettability. Mm-hmm. So if you can imagine a water droplet sitting on a non-stick Teflon frying pan, it will sort of sit there and roll around really easily. But if you put it on sort of a sheet of really clean glass, it will spread out. So it's that sort of spreading outness. It's called, if it spreads out really easily, it's called hydrophilic or water loving. But if it sort of stays as a ball, it's called hydrophobic or water hating. So that's can be down to both the surface chemistry and also, interestingly, the actual physical microstructure of the surface, or what it looks like under a microscope. Because using chemistry alone, you can get sort of droplets that sit on they're a bit like hemispheres, but you can't get them to ball up anymore. But if you get a rough surface and that surface chemistry is hydrophobic or water hating, it can ball up into nearly a perfect sphere and roll off. Mm-hmm. And that's down to this interplay between both chemistry and the physical structure of the surface.
Does that have to do with the lotus effect, where it's like it more likely to interact with itself than the surface that it's on?
That's absolutely spot on. That's where they developed the effect. It was in Germany in the mid-90s. This effect was discovered and patented. And yeah, it's termed the lotus effect, because that lotus leaf, if you look under it in a microscope, is like lots of really sort of bumpy pillars. And those are all made of a naturally occurring wax. Mm-hmm. And so when the water droplet sits on that, it would prefer not to spread out on that surface, and so it balls up, because water's got a very high what's called surface tension, or sort of the skin of that liquid is called that's effectively what sort of surface tension is. Sort of the higher the surface tension, the more force you need to pull, the force you need to stretch that droplet out. So yeah, that's sort of how the water balls up really nicely. And you can actually sort of feel the surface tension if you go and have a bath and or fill up a sink, put your arm in it, you can feel that grab of water on you, and that's the surface tension. So yeah, water's got a very high one, and that just allows the droplet to roll off. But if you put a droplet of oil on there, and the oil loves this waxy surface, that will spread out even more than it would have done on a flat waxy surface. So it's almost sort of, if something's super hydrophobic, like the lotus leaf, so extremely water hating, it would tend to be super oleophilic, where the oleo bit refers to oil. Mm-hmm. So if you sort of think of the scenes after sort of like an oil spill at sea, you'd often see seabirds caked in oil, and they can't actually get that oil off them because their feathers, water will roll off them because the feathers are hydrophobic, but the oil seeps in and can't be removed. And unfortunately, then these poor seabirds can't just drown because they weight of the oil in their feathers. So nature's got an awful lot to sort of inspire materials development from. It's amazing.
So I guess you kind of did a deep dive into the surface tension, but one thing that you have told us about is the idea of pushing boundaries as a motivation to pursue research. And so it sounds like we've learned a lot of this through research, but what pushed you or motivated you to get involved in research, and in particular material science research?
Okay, I think it was sort of to get into sort of research, it's sort of like learning new stuff and sort of just, I know it sort of sounds childish, sort of playing in a way. It's sort of like, if you sort of tweak one thing, what sort of effect does that have on either something else or that overall system? And so, yeah, it's that sort of like learning and almost sort of like playing with new toys, sort of like in my case, of like the microscopes. I mean, I used electron microscopes and also atomic force microscopes, which are sort of like little needles with atomically thin at the end that can sort of actually see atoms with. And it's that sort of being able to sort of see things you can't see with your naked eye is just absolutely fascinating. And I think it's and then with the sort of like the using chemistry to be able to change what you can see under a microscope is also fascinating. So it's, some of the other research that I did was to make tiny little squares on a gold surface. So I made these gold pillars by using a technique called micro contact printing. So this is essentially, you may have done something called potato printing as a kid, where you get a pattern on a potato, you cut it out, put paint on it, and stamp it on the surface. This is micro contact printing is essentially the same, but on a much finer scale, where you can get features of a millionth of a meter. So what I did was to make a stamp with these tiny little features on, put a chemical on there, and then stamp that on the surface of gold, of a really thin layer of gold, and then that would have a chemical pattern on the surface. And I would then etch away the unexposed gold using it was a mixture of chemicals, and this would just leave little pillars of gold that had this protective chemical layer on. And then when I saw that for the first time under a microscope, it's like, wow, I made that. That is amazing. So it's that sort of, it's just wonderful, that sort of whole using sort of chemistry to remove material and then seeing it under the microscope. It was great.
Yeah, that's awesome. I remember in my first year of research doing energy dispersive spectroscopy, EDS or EDX, and just being able to see, oh, this region is this element and this region is like this element was really cool. And being able to, like you said, go down to like a microscopic or even nanoscale level to see the surface of a material was just really cool, really interesting. And so I wanted to dive into that a little bit more. I know that, with the surface of the influence of surface on the properties of materials, especially with nanomaterials, that surface area to volume ratio is very influential and can dictate several interesting properties. So I was wondering if you can explain why so many researchers hone in on what exactly happens on that surface of small scale materials and what innovations have come from this?
Okay, well, from my sort of research, I made gold nanoparticles as part of my PhD, and due to their small surface area, they're in fact red. That sort of scale. So that's one sort of influence that the size can have, but it's also because of that sort of high surface to volume ratio. You've got a lot of atoms at the surface, and they're at higher energy than those underneath. So you've got different energetic levels, and for example, and these can be more reactive, so used in catalysis because they've got the high volume, a high surface to volume ratio, and so can be used for different chemical processes that way, and sort of speed up reactions, which at the moment, with all the environmental issues, the sort of scrubbing of factory fumes, for example, is of great interest. So that was one of the things where you can get that, but also using the sort of optical properties of, like, say, quantum nanodots in displays. So you've got these organic LED or OLED displays, and these are, if you look under the microscope, you've just got these tiny clusters of atoms basically making each pixel, so you get this really high resolution screen. So there's some examples anyway.
Cool. Well, another application that we've talked about previously involves micron scale chemical sensors that are sensitive to anthrax. So you were mentioning this a little bit earlier with COVID, but could you kind of dive into this example more, and what impact could this surface technology have in the future?
Yeah, as I alluded to, I worked with a group in mechanical engineering here at University of Birmingham on a project where they made these sensors that were 200 nanometers thick, and they use a focused ion beam of gallium ions to literally cut these out of a membrane of silicon nitride. And they effectively look like paddles, and they were suspended on both ends, so they could move in a sort of torsional vibration. And around the edge of these paddles, they put a nanometer thick layer of platinum wire, so we could conduct electricity around and control that vibration. So the idea was to vibrate it at a given frequency, and once I'd put a chemical layer in the middle of this paddle that was sensitive to, we actually tested out on gold nanoparticles, but the idea was to go down the anthrax detection route. When another chemical species is stuck on that surface, it changes that resonant frequency. And so you can, by working out the difference of the resonant frequency with and without that absorbed chemical on there, you can work out how much stuff effectively has been absorbed on the resonator. And if you've designed it so it's specific to, say, anthrax, you'd be able to work out effectively how many anthrax molecules it's detected by knowing the weight of it, the overall weight detected, and the weight of one anthrax molecule. Yeah.
I have a quick question just about that. So, like, if it's dependent at least a little on the weight, then how do you know if it's like anthrax versus some other molecule? That's just one thing I was confused about.
You'd design. The idea was anyway to design a chemical that we would coat on the surface that would have a region of chemical groups that would be specific, or as specific as we could make them, to anthrax. So the anthrax, it would only be anthrax or something similar would stick to the surface.
Got it.
So if we saw that there was something being absorbed there, we could then take that away for further testing. And the idea was for these devices to be just be really small devices with all the equipment to work out the mass detected. I mean, that wasn't my part of the project. I mean, that was for the engineers there, which is great example of collaborative research and why you can never do these things on your own. But unfortunately, the project along the Anthrax route wasn't actually funded, but we did the proof of principle of that experiment using gold nanoparticles. But yeah, the idea was to look down the Anthrax route with a view to making these small devices that could be like put around airports, because this was about, when was this? It was about, I'm going to start showing my age soon, about sort of 10, 15 years ago or something. When there was actually sort of a real danger of sort of anthrax being brought over from Asia, just in sort of like drums and stuff, just naturally occurring anthrax. So it was, and also the sort of terrorist threat of an anthrax attack. So it was a case of, it was quite topical at the time, but now if we were to design one, it would be more along the lines of detecting COVID, I think.
And so the way it works, if I understand correctly, is like we know the resonance frequency like of just the material, and then as more anthrax gets collected, it slows down the resonance frequency as it grows in weight. But how much does it slow down? Is it like an easily detectable change, or like, I guess, like what's the limit of this technology?
The design of the paddle we were looking at can detect picograms of material.
Oh, wow. Okay.
So it was sort of shown to that. I mean, off the top of my head, I've forgotten how many molecules of anthrax that would have been, but it was pretty sensitive, and also had a high Q factor, or by Q factor I mean on the signal it was a very sharp signal.
Okay.
Anyway, so that was done by the sort of clever people in the mechanical engineering department. Mine was just to do the surface chemistry bit. But it's, sorry.
No, I was just wondering, do you think, like, I feel like as time evolves, unfortunately, like, bioweapons can get more complex, they can differ. So do you see an opportunity to have these microsensors that are sensitive to multiple different potential bioweapons or like different materials instead of just one?
I think it might be a case of if you've got, you might have to sort of use a sort of combination of sensors, sort of like with a sensor being specific to one kind of bioweapon, perhaps. But that's probably one of the approaches to do it. I mean, that's not my sort of field of expertise, sort of like bioweapons. So I don't want to sort of say anything sort of out of turn on that, but that could be one way. Yeah. I know there was a lot of research into using sort of arrays of resonators, known as sort of like electronic noses and that kind of thing. So
that's really cool.
I know it's awesome.
Yeah, no, that makes sense that it would just be like a different sensor for different things. But now we can move on to something maybe more relevant to like the water repellent surfaces. And you mentioned the idea of modeling water repellent soils, as hydrophobicity versus hydrophilicity can dictate soil erosion, which can ultimately lead to worse plant cultivation and growth. And so I was just wondering if you knew what parameters can come into play when you're modeling those water repellent surfaces, and just like in general, how these models can be used in agriculture applications.
Okay. So yeah, going back to the discussion earlier about the lotus leaf, the way that was it's got a bumpy topography or surface texture, and it's got a water repellent waxy coating. If you looked under the microscope at a soil bed, that's also bumpy, and then after stuff like wildfires or pollution, it can get sort of like oil deposited on it, which would then make it hydrophobic chemically, and then that roughness makes it sort of super hydrophobic or water repellent, and then the water can roll off it. But if you think of like a rack of pool balls, and then you put another rack on top of that, some of the bottom layer will be sticking up slightly into the top layer. So the way that soil scientists model this is, if you've got the water level coming through that top layer, it will automatically be sucked through into the bottom layer once it touches the top of that bottom layer, if you get what I mean. So the actual relative sizes of soil particles in the top and bottom layer could come into play as well. But the main disadvantage of this water repellent soil is that, as you quite rightly pointed out, it can lead to like plant death because they can't get hydrated, but it can also lead to enhanced soil erosion. So if a droplet of water goes onto a very dry water repellent soil, it can actually, the surface tension of that water droplet can lift these tiny soil particles up and roll off and carry those away. So you might see this if you are into baking or anything, or you've got like a bowl of flour and you put a water droplet in, that droplet gets coated with flour particles. So that's very similar to the water repellent soil, and that's formed what's called a liquid marble. So it's got a liquid core surrounded by a thin layer of particles. And if it rains on this bed, you get lots and lots of these liquid marbles that roll off and can basically remove many layers of soil. But one way you can remedy this is by lowering that surface tension of water, so it goes onto that top layer and then can more easily penetrate that bottom layer. So one way you can change the surface tension is by using surfactants or soaps. So if you got actually, this is another way of overcoming the hydrophobic effect of a lotus leaf, is if you put a drop of soap solution, that could actually penetrate those the bumpy surface of a lotus leaf. So this is that, again, this that sort of interplay between sort of something very, very physicsy, which is like the topography and that surface tension, and also chemistry as well, being the chemistry of the solid surface. So it can be quite, it's a very complex system, but there's
what exactly does that interaction look like between like a hydrophobic surface and a surfactant? What exactly about the surfactant makes it lose the other material lose its surface tension?
Okay, so if you think of water, you've got lots of OH hydroxyl groups in there, which that's what gives it its really high surface tension, because you've got all these attractive forces in between all the molecules. But if you put a surfactant in there, a surfactant is a special molecule that one bit of it loves water and one bit of it hates water. So it's a bit like it's used as soaps to basically, when you clean your hands or your dishes, the water hating bit sticks on the oil or dirt, and then the water loving bit of the surfactant sticks in the water and effectively pulls that dirt off your hand or your plate. And if you've got a droplet, these surfactants sit at the air-water interface, or air-liquid interface. So it sits on that bit between like the liquid and the air, and that just reduces the surface tension because it disrupts the forces of the liquid itself that's trying to hold it together. So it's a fascinating field, and that's what sort of can help sort of stabilize foams and things as well.
I guess.
So,
going back to a previous conversation, you said that like the entire world are just surfaces, and so when we think about using this for agriculture, we're talking about like acres in like the magnitude of order. But then you just talked about gold, which was on like microns and not less. Does our approach change based off the scale, or like we just talked about how nanoparticles, but like after nanoparticles from microns to acres, is it like a generally linear scaling technique, or do we continue to see different surface properties at different levels of length?
I'm not quite sure.
I guess, does our approach change when we're talking about huge scales, such as like a dirt field out in the countryside, compared to a gold surface that we're stamping like this chemical structure onto?
Do you so it's sort of, if you've got say a gold nanoparticle, it's and if you compare it to say bulk gold, as that particle gets bigger, it will become more and more like bulk gold, and then at some point, it doesn't really matter how big it gets, it will still look gold and have the properties of gold. So yeah, I mean, my sort of expertise is not when stuff gets absolutely massive, but again, this is the sort of amazing thing of how important length scale is. I mean, whether it's actual sort of like physical lengths or time lengths or stuff, because again, with high speed cameras, you're looking at really short time scales compared to if you're looking at time lapse. But in answer to your question about sort of like acres, I'm not really too sure on that. There wouldn't be much difference between sort of like an acre of, say, gold or like a centimetre of gold, but there would be between a centimetre of gold and a nanometre of gold.
No, that answers the question.
Yeah.
I'm just very curious. So like at smaller scales, there's larger changes, but
Mm.
at some point it's just gold.
Yeah.
And we can kind of model it the same. Okay.
I mean, it's when you're getting the sort of quantum effects and again, that's beyond me. Sort of, I think that's one thing that possibly sort of totally confused me in my first year of chemistry was when they were talking about the sort of quantum theories and stuff. I mean, it takes a clever person than me to get my head around that, to be honest.
Okay, well, one more interaction that we thought would be interesting to talk about is how foams react with hydrophilic versus hydrophobic surfaces. So we know that we have like fire-floating foams, and we also have like foam at the top of your Guinness beer. On a microscopic level, what does this surface interaction look like? And maybe for a little context, like what impact does different types of foam have on our everyday lives?
Okay, I'll start with the second question, if that's all right. So, sort of, as I alluded to earlier, when you've got surfactants in water, you make that water droplet stretchier. And for foams, it's that sort of stretchiness of the water that sort of captures air bubbles. So that's how effectively foams are made. So you'll notice you washing machine, be it your clothes washing or your washing up bowl, you'll have layers of foam there. Those are just because you've got surfactants there. Those foams don't really do the cleaning. Most of the cleaning is in the solution of the surfactants there. So that's probably where most people have come across surfactants, or if I mean, as a child, I remember blowing bubbles a lot as well, and I'm sure many children. So it's not just this side of the pond that blow bubbles. I'm sure you guys do too. And it's having that surfactant in there that helps make the water stretchier, and you get those beautiful sort of like wind socks sort of thing before the bubbles close up. So that's one place you'd have come across foams. But also in the animal kingdom, there's some tree, I think they're called the Thundara tree frog. They make foams up in trees to lay their eggs in, and their tadpoles actually mature in foam up in a tree, which is rather awesome. So, and also at some seasides and beaches, sometimes you get foams that are generated at sea that blow in and cover whole beaches. And this is due to bits of seaweed and naturally occurring surfactants that are in the sea that that then stabilize all the air that's trapped by waves and create these massive foams. So foams are everywhere and they're great fun. But the sort of research that I did when I looked at the head of killing the foam in Guinness was inspired by a book I was proofreading. It was just about foams, but they were talking about anti-foamers. So anti-foamers are often put in normally chemical additives that are put in formulations to kill or to stop unwanted foam. So for example again is your clothes washing machine at home, because one thing you don't want is tons and tons of foam to come out of that and pop out of the drawer and cover your kitchen in foam. So they actually have anti-foamers, which are often sort of silicone oils that are within the formulation of your washing up your detergents. And so I sort of thought that I was reading this and I thought, what about solid anti-foamers? Sort of like, I mean, Guinness has got its famous head of beer head on there. What about if I coated the glass in a hydrophobic material? Just then it might just be out of interest. And so I did this. I got this waterproofer for just for raincoats, and I coated this on the inside of a glass, poured Guinness in, and I noticed, the famous Guinness head was no longer there. But what was there was on the inside of the glass, rather than it just being tiny little bubbles, with these huge bubbles. So it looked more like sort of like fizzy pop than Guinness. So what I think is going on there is that if you look under like a microscope at the surface of the glass, there's tiny little micro cracks there. So what would be happening with these would be perfect nucleation sites for the dissolved gas that's in Guinness beer to nucleate, form a bubble, and then if you got your normal hydrophilic glass, so uncoated, the liquid would wet the inside of that crack and force that bubble out. Whereas if you've got a hydrophobic surface, the air bubble would energetically prefer to stay in that crack rather than the liquid going filling the crack and displacing the bubble. So that's why I sort of think that was sort of causing those sidewall effects. Regarding the actual foam head, that itself, needs a lot more investigation, because after being really pleased with myself that we'd managed to kill the head of Guinness, me and like another guy in the lab, we went to a local brewery to try it on other beers. We spoke to the master brewer. He poured a few pints, and it only seemed to work on the Guinness on that sort of head thing. So it was one of those. I mean, beer, like a lot of things, is such a complex system. It's just basically a big mash of you've got different proteins in there, different acids. So it's one of those that I would love to sort of spend more time investigating it all, to be honest. But but the sort of applications we had in mind were things like bottling lines for sort of fruit juices. So if you've got like glass bottles being filled with fruit juice going through at hundreds of seconds, just high speed things, when the juice gets injected in, it often creates lots of unwanted foam. So there are ways of getting rid of that foam, but I was sort of thinking it might be quite an interesting application if it worked.
But for sure.
But one of the ways they do get rid of that foam is by ultrasonic methods as well. But I was just looking for an alternative.
No,
so you never know when it comes in handy.
Yeah, no, that's really interesting. And I could definitely see it being used in more of like the behind the scenes processing type methods. But it's really fascinating to me, the psychology of consumers, where also it's like, if they don't see that foam head on a Guinness beer, they might be more deterred. They're going to be like, something's wrong. Or like when you're washing your hands with soap and there's no bubbles, I would think, oh, this is like bad soap or something like that. So that's always fascinating. And it kind of ties into that point where foams are everywhere. We just may not realize it.
It is, oh, definitely. Yeah, and as you said, there's so much psychology on that. There's the collaboration between science and psychology, as well as sort of different kinds of science. It's just fascinating, to be honest.
For sure. Yeah, maybe David, we should do like a material science and psychology episode. I feel like that would be cool.
Yeah.
But now we can move on to, I guess, what you're involved with now, which is material science outreach and the Discover Materials program. And so I know you love this. I know you love outreach. And so I was just wondering what drew you towards this side of things and what is next for Discover Materials.
Okay. So yeah, the outreach I absolutely love, and I got started on it when I was doing the research into the water repellent soils, and I was working with an outreach project at Nottingham Trent University called Nature's Raincoats, where we'd look at the lotus leaves and how we can learn from nature. And I was going around some of the science festivals in the UK. Went to the Cheltenham Science Festival, which is a really good one. And then I had a chance to go to India to take part in Tech Fest 2012 and took the lotus leaves out there. And it was just phenomenal. So it's just that what I love about outreach is when you talk to, or be it a school child or one of their parents, and you just see their eyes go, wow. And it's that sort of almost that there's something just clicked in there that you've engaged them, which is absolutely wonderful, which is the main reason I love outreach, to be honest. And then it actually sort of ties in nicely with my background of getting into materials and how I found materials by quite an indirect route. But I'm by no means the only person who's found it that way. I mean, the more people I talk to, a lot of them more and more seem to have a chemistry background but didn't know about materials. So this Discover Materials group, we're wanting to work with school students, their teachers, and also their families to make them aware of material science, really, because, as you know, materials are everywhere. It's just basically knowing what stuff's made of, how it works, why it's used, and also how you can use these materials to solve some of the huge global issues like medical devices, energy sources. It can all be helped and solved by material scientists, and people often haven't heard of them. So what we're doing, we're working on a new website which will be launching soon, which will act as a gateway for the target audiences, I've said, but also put a face to material scientists. So we've got a cohort of PhD and postdoc students and a few outside of that who are our Discover Materials ambassadors. So they've each got a profile page on there. So the school students can find out more about them and why they love material science. And there'll be information about our upcoming events, but also there'll be resource pages about that will focus on videos and other media that we've made as a group, but also information about sort of various topics of material science and external links and stuff like that. So that's some of the stuff we've got upcoming is mainly our website's the big one. And also we've got our Halloween event, which will be happening next week while I was dropping the pumpkins and recording them. And we'll be doing winter events as well. But it's mainly trying to engage with schools and empower and infuse the next generation of material scientists, really. Because at least in the UK, the number of people doing material science at universities is sort of a good factor of 10 less than those doing other sciences and engineering, and that's probably being generous.
Yeah, that sounds like an awesome time, both with the website and all these events coming up. But I guess maybe to wrap it up, we discussed the fundamentals and applications of materials whose surfaces have strong influence on both their properties and performance, and as well as your passion for outreach. What advice would you give to the next generation of material scientists who strive to push boundaries and make a lasting impact on the world?
Well, first of all, sort of advise to sort of appreciate the materials around them and be curious, to be honest. I mean, one of my favorite bits of outreach kit is this little clip-on microscope lens I've got for my smartphone, and you can just sort of see at times 60 the world around you. And when I've shown this to school children, they love it. So it's just being inquisitive, really, and then it's just go with what interests you, and because it's pointless trying to get someone to be a material scientist if they've got no interest in science and their interests are elsewhere. But you just need to make people aware of what they can do and what they can be interested in, really. It's in that inspirational game, to be honest. So it's advice for any kids out there is just follow what you enjoy and make the most out of it, and just be interested and ask questions, to be honest. You never know where it might lead.
For sure. That curiosity gets you very far along. So totally agree with that advice. But thank you so much, Chris, for joining us today. It was a pleasure having you on. Learned a lot about surfactants, foams, and just the surface properties of materials in general. So thank you so much. And we hope you have a great rest of your day.
Brilliant. Thank you very much.
Thank you for tuning in to this episode of the It's a Material World podcast. If you enjoyed the show, consider subscribing and hitting the like button down below. And if you'd like to support us on this journey or simply show off your love for MSc, we actually released merchandise And if you'd like to check out more of the designs, visit itsamaterialworldpodcast.com/shop or use the link in the description. We'll see you soon. And in the meantime, go change the world.